Okay, so I'll start recording, and I'll just start this lecture by doing a brief recap of what we covered in the last lecture, and then I'll see if you guys have any questions, and then we'll move on to finishing at least the part that we started with the different interest schemes, simple and compound, and then we'll move on to talking about economic equivalence. Okay, so these are our objectives for this chapter, and as I said, it's a very important chapter, and it's also a fairly lengthy chapter. However, the concepts are very basic, and they kind of repeat over and over again. And so we said that our goal is to understand the time value of money, why we need it, why it's there, what causes money to have a time value, and we already kind of saw that in the last class. And then we wanted to show you how to plot cash flow diagrams, which graphically represent cash flows, money going in and going out of your account, for example. And then we started talking about two different methods of calculating interest, simple and compound, and that's where we'll continue from today. And we're also going to be talking today about the final concept in this chapter, which is called economic equivalence. So when are two cash flows, when are two alternatives equivalent? And we discussed this example at length, and we saw that we have a decision problem with two alternatives, and we saw we motivated kind of why we have an issue comparing these two options. It's because we're valuing two different things, right? The amount of money and the time at which you receive a given sum of money. And we said in order to make comparisons, we need a way of valuing money at different points in time. And how are we going to do that? Well, we're going to move everything to the same point in time, and that would make our comparison very straightforward, because we compare money at the same point in time rather than different amounts, possibly at different points in time. And we talked about why money has a time value. We said because of its earning power, right? Because of investments and interest that money can accrue, and also because it loses purchasing power over time because of inflation. And so the interest rate is the key thing here, which is what is going to allow us to basically move money or find out how much money, or I'll put it this way, we will find out the value of a given amount of money at a particular point in time in today's dollars, for example. So what is going to allow us to move money from the future, for example, to the present and back if you want to. And we're going to see how we do that actually using equations and stuff today. And we talked about what interest is. It's basically the cost of borrowing money, right? And we said these are examples of why the bank might charge interest if you take out a loan from the bank. And we said that always you will have inflation, or in most cases, at least generally speaking, inflation always exists. Sometimes it does not actually, but the norm is that you have inflation, so things get more expensive and your money loses purchasing power. And so whatever investment that you take, your earning rate from that investment should at least keep up with the inflation rate in order for things to make sense, so you don't lose money over time, basically. And then we started discussing cash flow diagrams, and we gave examples. So here's an example of a cash flow diagram for a loan from the perspective of the lender and from the perspective of the borrower. These arrows indicate either money going in or money flowing out. And then we indicate time on a horizontal axis. And we said that we always take the net. Some questions you will be specifically asked to draw the net cash flow, but I think in general you should always think about net cash flows or net cash flow diagrams as opposed to just regular cash flow diagrams. And we said what this means is that if you have money that is incoming and money that is outgoing at the same point in time, you just take the net amount, right? That simplifies things. And then we talked about these very important terms that we're going to use, which are principal, which is the initial amount of money that is involved in an investment. For example, the interest rate I, the interest period, which is basically how frequently your interest is going to be accumulated or applied to the principal amount. So this could be years or months. And also the number of interest periods, so the number of times you apply the interest. And then a sub n is basically telling you at each point in time or at each time period n what sort of amount is coming into your account or is leaving your account. And finally, the future amount of money is the value of the money or the value of the principal, for example, after it accumulates interest for a certain number of interest periods and where the interest rate is little I. And we gave an example. We saw how we can draw a net cash flow diagram in the case of the loan, right? So we subtracted $300 from the 30,000 here because we're interested in the net cash flow diagram. And then we started talking about simple interest and compound interest, which is where we kind of finished the last class. So before I continue here, any questions on the material that we covered last class? Okay. So we started talking last class about simple interest and compound interest. And so we said simple interest, the difference between the two is how you compute the interest. And so simple interest is basically the following. Each time period when you invest, for example, a certain amount P, the interest that you're going to earn is simply I times P. So interest rate times the principal. And so this is fixed regardless of what year you're in. It is always calculated based on P. Whereas with compound interest, from year to year, you actually get a little bit more every year. So I'm actually not going to write down what's happening here because we're going to derive the formula later on. But hopefully you understand that with compound interest, the interest that you earn in a year, you can also invest that, and then you get interest on that interest. And so money earns money. And we said that it's the most popular interest scheme, and almost always we're going to use it unless we state otherwise. Unless I state, for example, use simple interest, then you should always assume the word interest refers to compound interest. And we gave an example here. We started with simple interest, and we did things in a table step by step. So again, we said always the interest earned in the case of simple interest is going to be I times P, where I here is 8%, so it's 8% times $1,000, and it's going to be $80 every year. It is always fixed because it's always the same value IP. In order to put this in a formula, we said that we have IP in every time period. But then how many time periods do we have? We have n time periods. And so the formula is going to look like this. The future value of the money, which is this final value in the table, is going to be equal to the principal, which is the initial investment that you make, plus this extra interest that is earned. So this here is the interest, the total interest that is earned over n time periods. And so you can see here it's IP, the fixed amount, times n, where n is the number of time periods. Very straightforward. And sometimes you will see this, of course, written as the following. If you take P as a common factor, you'll see it maybe like this. But again, we're not going to see this very often. Simple interest is not something that is going to come up very often, but you should be aware of it because it's used in some cases like bonds, I think. They will use simple interest. But generally speaking, in investments, you will always use compound interest. Okay, and so now that we know this formula, this is kind of exactly where we stopped. We can go back to that example. You see here the same table that we just had. And now we can compare our answer and see if we use the formula, if we get the same answer. And the answer is, of course, yes, 1240, 1240. Right, so this is going to be P. P is the initial investment, and we already know it's given in the problem. This is I, this is P again, and this is N. So just straightforward plugging in the numbers, and you get the same final answer. So the formula provides us a much quicker way of finding the future value of our money or of the investment compared to using a table, especially when the interest rate is always going to be the same from one period to the next. What about compound interest? So we're actually going to look at the same example, same parameters. So we're given the same present value. You're investing $1,000. The interest rate is actually going to be the same, and the period is actually going to be the same. The difference is, again, how you would compute interest. And so here's what it looks like. So in the beginning, you have $1,000, same as before. And in the first year, nothing actually changes, right? Because in the first year, it's still going to be the interest times the principal. So IP like before. And that's why you get 80. And then you add that to the $1,000, and your ending balance at the end of year one is going to be $1,000 and $1,080. What about the second year? That's where things start to change, right? Because now, instead of just doing IP again, now you actually have to look at this value and apply interest to it. So now this value here is gonna be 8% of this value here. Because you're $80, you're also earning interest on that extra $80. And that's why this number is a little bit increased, right? It's not 80, it's 86.4. And then once again, so this is the interest that we earn in this period, we add that to this number here, and we get this value, and then we do the same thing again, but notice how our interest is growing from one time period to the next. Why? Because we earn interest every time period, and we invest that, and we earn interest on that interest. And so that's why it keeps growing. And so this value here is higher, of course, than the 1,240 something maybe that we saw in the table from the simple interest case, which makes sense. Can we come up with a formula for this case? And the answer is yes. I mean, it's a little bit more involved maybe than the last one, the simple interest case, but we can still do it. And so if you look at what happens, at time 0, n equals 0, we start with P. This is the principal amount, right? This is today. I'm investing this money today. Now in time period 1, what's happening is that I'm applying, so I'm taking my P and I'm adding interest to it. How do I add interest? Well, I can just multiply by 1 plus I, and hopefully you see that, right? Because this is just P times IP, P plus IP, sorry. Right, so this is the principal plus whatever interest the principal earns. And you get P times 1 plus I. So this is F1. So what F1 means is that it is the value of your principal after one time period, after applying interest for one time period, right? What about n equals 2? What's going to happen? Maybe someone can tell me what happens when n equals 2. Yes, Khalid?
Take the whole value that I got from n equal 1 and apply the interest on it.
Yes, and what does interest look like? How do I apply it?
IP. So it will be plus IP multiplied by IP. Or
yes, yeah. Another way we can do that is the following. You just apply the 1 minus I to the value that you got from F1, which is kind of what you were saying, but you were using IP, whereas, I mean, I think here it's maybe a little bit, if you understand where this is coming from, here it's a little bit easier to follow, maybe. Depends, but it's the same thing, exactly right. And so F2, the future value, so we're going now from year 1 to year 2. We take the value in F1, and then we apply interest to it. Again, you could just multiply by 1 plus I to whatever value you had from F1. What is F1? Well, F1 I already know, it's P times 1 plus I. And so it's P times 1 plus I times 1 plus I. So it's P times 1 plus I squared. And you can see that inductively, if you keep going, you'll always find the following. That F, you can also add a little n here, actually, like a subscript, if you want to. No, actually, no. So this is more general. I'm not sure why they put n equals capital N. In any case, so the general formula is as follows. So just look at this part here. The future value of your principal is going to be P times 1 plus I applied capital N times, where capital N is the number of interest periods that sort of your principal accumulates interest in. Okay? And so that's basically the general formula for this case. So to compare it with what we had before, if my memory serves, what we had before is something like this. Okay, so they're a little bit different, but kind of similar. But this is the more general case, and this is probably the most important formula that you're going to learn in this course. So this is, you can call it the fundamental theorem of engineering economics if you want to. So this you should memorize, I think, and through practice you will. There are other formulas that we're going to see maybe in next week that you may need a formula sheet for because they get a little bit complicated. However, they're all derived from this fundamental theorem or formula. So this one we're going to see very often. Hopefully it becomes second nature to you. And when you need to find the future value of a payment, you just plug in depending on what n is, what I is, and what p is, and you can find the future value of a payment. And so what's going on in this example? So to see things graphically, we invested $1,000 in time 0. In time period 1, we got 80%. We got $80 extra, which is 8% interest. But then because the interest is compound, we can take that whole value, invest it, right? Invest it at time 1, and at time 2, it's going to earn even more interest. And so we're going to get this total. And same thing again, we can take this amount here and then invest it at time 2, and it's going to earn interest for us, and then we get this value, which I think was the final value that we saw in the table. And so, but now that we know a formula, we can try using the formula to compute this and see if we get the same value. And the answer is of course yes. And so if you use this formula that we just derived, plug in, we need to find f. We're given p, which is sort of, p by the way is principal, but sometimes it can be the present value of a sum or of a payment. Because you remember f is future value, so you can always think of p like the present value. And in fact, I think we're going to use p as we're going to like use p to represent present value more so than just principal, I think. So you can think about f and p, and maybe it's easier to remember instead of thinking about future value and principal, just think about future and present value. So the present value of our investment was 1,000. We know the interest rate is 8%, and we know it's been applied for 3 time periods. And so just plug in, you get the same exact answer. So it gives us a quicker way of finding what f is rather than using a table. All right, so that's compound interest, and now we're going to see a few examples on it before we start talking about economic equivalence. Right? Oh, so this is what the cash flow diagram looks like for this example. You invest 1,000 and you get this amount back at time period 3. Okay, so here's another example. Now, suppose you deposit $100 now. So now meaning a time or at n equals 0. But you also deposit $200 2 years from now. So n equals 2. And you deposit this in a savings account. Remember, savings accounts, they are bank accounts, but they earn interest. So you put your money in there and they give you, actually 10% is rather high for a savings account, but this is just an example, so it's fine. But normally it's going to be something like 1 or 2% max, I would imagine. And so the question is, how much will you have if you withdraw your money at the end of the 10th year? Okay. Now, it's always instructive, it's always nice to see what the cash flow diagram looks like, because sometimes like when you're dealing with a word problem, you may lose things. So once you graph what it looks like, it becomes easier to follow and to see things at a glance. And so that's what the first thing that we're going to do in this example is we're going to actually plot the cash flow diagram. And so I want your guys' help. So I'm going to draw what roughly looks like a horizontal axis, and I'm going to indicate 10 time periods on it because that's the scale of our investment, or that's sort of the horizon that we're working with. 6, 7, 8, 9, and then 10. Okay, now what should I put on here?
A deposit, which is an arrow going down.
Down.
Where should I? Yeah, where should I put that?
And 0.
Put 0. 0.
Right, so I put an arrow going down, which is exactly right. So this is a deposit. This is money going out of my wallet into an account. Anything else I should put? Oh, so chat, let's see what people are saying.
In 2, 321, I think.
Oh, so you're jumping a little bit ahead. So remember, right now what we're doing is we're just translating the words into a diagram. So we're not yet computing interest. I just want to see what the problem looks like, what the investment pattern looks like, and then I want to compute the interest maybe and find out what happens later. So someone said in the chat, $200 in time 2, which is exactly correct, right? So remember here, we have $100 now, which we just plotted, and you're investing $200 2 years from now. So at time n equals 2. So I'll just plot that at the moment. I'm not computing anything, I'm just plotting, right? So I'm going to make this arrow a little bit longer, and I'm going to put $200 here. Yep, and the arrow goes down again because it's a deposit. And I can just indicate the interest rate on this plot just for completeness. What do I need to find? Can someone tell me what the problem is asking me to find?
What would I have at year 10?
Yes. And so is there a way to draw that maybe?
Maybe we put a question mark at 10, maybe.
Okay, yeah, but if I so yeah, so at 10 you're saying put a question mark because I don't know the amount, right? Is that right?
Yeah.
Okay, yeah, so that's good.
Yet,
But then
yeah, I want to calculate 10.
Exactly, which is F, by the way, right? So I'm gonna write here F, the future value of my payments. I don't know that, so that's what I need to find. Now, what is F representing? F is, if you think about it, it's actually the money that you're gonna withdraw at the end of the 10th year. And so if I were to sketch an arrow for F, which way do you think the arrow should go?
Up.
Exactly. Right? And so that's the cash flow diagram. So again, just to make sure everyone's on board, we first, I mean, you can put the interest rate so I don't forget it, it's 10%. But then we just translate the words into this diagram. So we say $100, I'm investing it now, so the arrow goes down. $200, 2 years from now, I find n equals 2. I put an arrow down, I put $200. And then I need to find, well, what else? Is nothing else, but I need to calculate how much I would have at the end of year 10. And how much I would have is how much I'm going to withdraw from my savings account at the end of 10 years. And so I'll put an arrow that is up to indicate a withdrawal. And then I'll put F, which is the future value, and I need to find F. So F is a question mark at the moment. I'm going to compute it based on the formulas. Okay? Any questions about what I did here?
Clear.
Okay. Yep. Okay, that's good. So hopefully this was easy to follow. And now I need to solve for F. First of all, I mean, I actually have the diagram here, which is exactly what we saw. Now keep in mind that this sort of thing, like these deposits and then computing a future value going up, this is very common, and we're going to see this a lot. Anytime you have, like, you're depositing money into some investment and then you expect it to take the money out after some time periods, it's going to look something like this. Of course, the amounts may be different, but it's generally going to be arrows going down a little bit and then one arrow coming up at the end. I mean, we'll see this a lot. It's not always the case, but this is very common, so you should get used to this type of thing. Now, what do I need to do to compute F? Let's see. What is step 1? So what do I need? Yeah, what do I need to do here in order to find F?
Compute P.
Okay, so what is P in this case?
The first is 100. After 2 years, it will become 121. So we
okay,
will.
yeah. So you actually do, yeah. Go ahead. Sorry.
So we will do the calculation after 2 years, which will become 321, multiplied by 1 plus 0.1 to the power of 8.
Okay. So yeah, that's correct. That's one way of doing it. And you'll see a lot with engineering economics with these sorts of problems. There are many ways to approach the same problem. And so you may take a different approach from your classmate, and you may find the same solution. And so that's why I'm going to be very skeptical if I see you guys all come up with the same solution methodology in every single problem. Because, I mean, the general principles are the same. It's just the steps. So what, I didn't catch your name, but what your fellow classmate was saying just now is he would compute the future worth of this $100 at time 2, and then he will add the 200. So he's going to apply interest to the 100 for 2 time periods, and he's going to get some amount. I think 121, right? Because the interest rate, yes, that's correct, because the interest rate is 10% per year, right? So if you do the computations, if you move the 100 by 1 time period, you're going to add 10%, and then you move it again, you're going to add another 10%, and you're going to get 121. And then you add these 2 numbers, and you're going to get 321. Okay? And then you need to move the 321 all the way here. You need to find how much it's going to be worth in the future. How do you do that? Well, you apply 8% for 8 time periods because we're moving it from 2 to 10. And that's going to be f. Okay, so that's one way of finding the solution. Another way is to do it a little bit differently. It's not very different, but it's just a little bit differently. So you first take the 100, and you know you're going to apply 10 periods of interest because you're moving it from 0 to 10, right, to the 100. And we know that from the formula it's going to be 1 plus 0.1, which is the 10%, to the power 10. And you can compute what this value is, and it's going to be 259. So I kind of skipped this step. I just went directly or straight from 0 to 10, which is fine. What about 200? How is that going to be different?
Calculated from 2, not from 0.
Exactly. So what's going to change? Well, the 200 is obviously going to change, but what else?
The period
8
will change.
it will be to
Exactly.
the
So
power
instead of
8.
10 here, yes, I will have an 8. So that's what's actually here in the next line. So the 200, of course, the amount changes. The interest rate is the same, but it's only 8 time periods. And so now I moved both of these payments separately. So I'm going to draw maybe another arrow here. I moved them to 10 years from now. And so this is what these payments are going to be worth. What's left for me to do?
Sum.
Just sum them.
Exactly. And why can I sum them? Like I couldn't sum these two numbers. I couldn't just do 100 plus 200. That's kind of wrong, right? But here I can sum. Why?
Because the 200 is not starting from 0. Therefore, you cannot sum them at the beginning.
Exactly. So another way of saying that is that they're not at the same time period. You're not summing. You're summing two different amounts, even though they're worth maybe very differently because they're at different points in time. Remember, because of the time value of money. But here, because I moved the one from 0 to 10, I moved the one from 2 to 10. They're both now at 10. I can just sum them. I can also compare them if I want to because they're at the same time period. Okay. So that's why I can add. So that's what justifies the sum, and then I find that the value is going to be 688. Now, if you follow this approach, you should get the same answer as well. And someone maybe, if you have a calculator out, you can double check. If you take the 321 and apply interest for 8 time periods, you should get the same thing. Okay. So hopefully everyone's clear on what we did here. Very simple example. I just wanted to make sure we go through it in detail. For some of the other examples, I will try to just gloss over them. As long as you understand the basics and the steps, you should be good to go. A question? Mustafa, yes?
I didn't understand. Where did we get 121 from?
Oh, so in this approach, what your colleague or classmate suggested is I take the 100, but instead of moving it, instead of finding its worth 10 years from now, I will just find its worth 2 years from now. And so what the 121 is, it's 100, and you add the interest, but only for 2 time periods, because you're moving it just from 0 to 2. Okay, and so that's going to be 121.
Oh, so I add them with the 200 because they are in the same period. Okay.
Exactly, and then you move them together all the way to the 10th time period.
Yeah, which will be 321 times 1 plus 0.1 to the power 8.
Exactly, and you should get the same answer. I actually haven't checked that, but you should. Otherwise, there's something wrong. Okay, and so those you see, there are 2 ways here of solving this problem. There may be even more, but slightly different ways. But you get the same solution. It's just the thing that matters is the concept and the principle. As long as you're following, you're making good steps, and you're justifying each step makes sense, then you should arrive at the same answer. So that's why I said if all of you follow this approach, I'm going to be a little bit skeptical because people think differently, and I just opened up the question and someone suggested this approach, even though what I had in the slide and what I was thinking about was this approach. So it's completely fine to use different approaches. Now let me erase the pen because things got a little bit messy now. So here's another way of writing things, and we're going to see this in detail maybe a little bit later. So P1 in this case is going to be the $100. And I'm kind of rewriting this same thing. So what I'm saying here is I'm going to take the $100. I'm going to multiply it by something. And this is something I already know is actually this, right? It's actually 1 plus 0.1 to the power 10, right? But it's written here a little bit differently, and we'll see why. And the P2 in this case is going to be the $200, right? And I'm multiplying it by something which I know what it is, which is this, and you can see it here in the next line, but it's written a little bit differently. And so what does this mean? This is sometimes called factor notation, right? So I'll write that here, factor notation. And we'll see it in a little bit more detail, I think maybe in this class. If not, then definitely in the next class. And so what this means, or the way you can read it maybe, or think about it, is you want to find f given p. That's what this slash is, or maybe that's how you can think about it. And then you specify I, which is 0.1 in both cases. And then you specify the number of years that you need. So this is like a functional way of writing things. So maybe you don't know the exact formula, and we'll see. Like for this formula, it's very simple. I already know I can just do 1 plus 0.1 to the power 10. That's exactly what this is. But in the future, we're going to see some complicated formulas. And so maybe it's sometimes useful if you don't want to write out the whole thing. Maybe you just want to use Excel maybe to compute it, or you have the function saved in a calculator or somewhere. You could just write it like this, right? This is just shorthand notation for give me whatever factor I need to multiply by specifying the inputs. The inputs are I, n, and that I want to find the future value given the present value. We'll see actually that sometimes you'll see p given f. Then it's the exact opposite. Maybe you're given an f, you're given the future value, and you need to go back in time to find what is the present value. And so then the factor is going to look a little bit different. Okay? And so one reason for writing it like this is because actually, at least in the past, I think, because I mean calculators weren't so ubiquitous, we didn't have them all over the place, we had to use tables for these things. So instead of plugging this formula in a calculator, just the textbook, if you look at Appendix B, I think, it has some of these tables. And so the way you can read these tables is as follows. There's going to be a table for every interest rate. And so we already know that for our problem, the interest rate is 10%. So I go and find the table for 10%. Okay? Once I find the table, I see something that looks like this, and then I need to do something more, right? So this is just going to be I. I'm still left with f given p and n. Those are the two other inputs that I still haven't done anything with. And so in our example, and we're going to see this in a little bit more detail. So you see here, we have single payment to equal payment series, gradient series. Now we're actually not going to cover these until next week. And so at the moment we have single payments, right? So if you go back here, P1, the $100, you can think about it as a single payment. And I need to find the future worth for that by moving it all the way to time period 10. And so I go and I see two columns here. If you look down here, one of them says f given p, one of them says p given f. Now I know I want f given p, so I'm going to look down this column. And then here's n. And so what I need to do is look for the value of n that I want. And in my case, it's going to be 10 for the $100. And it's actually going to be 8 for the other amount, for the $200, right? So I think if I skip ahead, these are the two values that I need to find from the table. And then if you look back, so remember, so these are 2.59 and 2.14. 2.59 and 2.14. It's exactly what I computed using the formula. Okay, so this is just so that you know there are other ways of finding these factors, especially if you don't have access to a calculator. I mean, these days that's very hard to come by, or very hard to for it to happen. Usually you would have a computer or a calculator or Excel even. So it's very easy to compute these values. You don't need a table, but just know. I just want you to be familiar with this notation because it's going to help us later when the formulas for these cases become a little bit more complicated. All right, there's actually a third way that you can find these values, and that is using Excel. Excel actually has some built-in functions for computing future values and present values. So for example, I think if you do FV, that's for future value, and you can see the inputs like when you actually type that in. I'm not like it asks you for the rate, for the present value, and for the number of time periods, and sometimes other things. And also, if you do PV, it's that can help you find the present value of a payment given its future value, for example. And so you can use some of these functions. And actually, in the book, I think they have a nice summary. So I'll see if I can scan that page and maybe upload a scanned copy so that you can see these formulas and maybe play around with them. They're very easy to use, and they're very convenient. Just know that I think if you want a future value, the present value that you provide has to be negative. It takes the convention that you're investing money maybe, and you're getting money at the end. So in order for your future value to be positive, the present value has to be negative. At least that's the way Excel sees it. It doesn't change anything. It's just a sign. Just make sure you provide a negative sign in front of the present value. Therefore, your future value is going to be positive. If you don't do that, then your future value might be negative, and you might be confused, like, why is this negative? But sometimes that doesn't matter, and all you care about really is the amount. The sign you can figure out from the context of the problem, and so you don't really care about that sometimes. Okay, so there are like at least 3 ways to find these values, either calculator, table, or using Excel. Excel actually will just do the computation, the complete thing for you. All right, so here's another example which we'll go over like a little bit more quickly. So you have this sequence of deposits, but you actually have a withdrawal here, so you're actually taking money out. And this is over a period of 4 years. Excuse me. And so the interest rate is 10%, and so they're asking what's going to be the balance at the end of the 4th year. Okay, and so what I need to do again is the same sort of thing. I need to move this payment to the future, move this payment to the future, so it's going to be 3 time periods, move this payment to the future again, and move this payment to the future. But then when I get here, the difference is going to be I'm going to add these 3 payments, but I have to subtract this payment because it's going in a different direction. Okay, and we'll see, I think maybe we'll see like a few approaches of solving this problem. So again, there are multiple ways you can approach the problem. And so here's the cash flow diagram again, and here's what here's one solution approach, which is actually what one of your colleagues suggested. You take the 1,000, you move it 1 time period ahead. It's going to accrue interest at a rate of 10%, and then you add the $1,000, and you're going to get 2,100. You do the same thing again. You move this forward, it's going to accrue interest at a rate of 10%, so you get 2,310. But then you need to subtract the 1,210 that is at the same time period, because it's a withdrawal. It's going in a different direction, and so you get 1,100. And then you do the same thing again. You move it 1 time period. Of course, this gets a little bit tedious if you do it this way, but it's still one approach that you can use. Then you add the 1,500, and you find the 2,710, and then you make the final jump to time period 4, and you get 2,981. Right? So this is kind of exactly very similar to what we saw in the last example. The only difference is that we have a minus here because the payment is going in a different direction. Another approach is to do what I kind of described at the beginning, is I take all of these payments and I move them. Now this one is going to be moved for 4 time periods. The second one is going to be moved only for 3 time periods. And then the last one here is going to be moved from 1 time period, only from 3 to 4. And here I can do this one too. This one's going to be moved forward for 2 time periods, right? So again, if we're going from left to right, if you're moving a payment from left to right, this is the formula that you should follow. And we're going to see the difference for the other case when we actually move something to the present, from the future to the present. It's going to be a little bit different. Okay, and so once I moved everything, I just need to be careful to subtract, right? So again, this is what you see here. This is moving the 3 bottom payments forward, and then finally minus this 1 payment that I'm moving forward by 2 time periods. And then because everything is at the same time period, again, I can just subtract. I can add and subtract. And I find the same value, 2,981, which was the same value as here, 2,981. Okay, so this is like a mathematical or analytical approach to solving this problem. A third approach that I can even follow is a tabular approach. Now this actually kind of looks very similar to this first approach. It's kind of the same thing. You're doing it step by step. But it's similar to what we saw with the simple and compound interest calculations. You have a beginning balance. You see what money you've added, and then if there's interest, you add it. So at the beginning, there's nothing, right? It's just a deposit, and that's going to be your ending balance. In time period 1, you take the 1,000, you apply interest to it, you find 1,100. But you also have a deposit in that time period of $1,000, so you need to add the 2 now, and you get this. And then you continue. Just make sure to subtract, in this case, in time period 2, because you're making a withdrawal. You see it's in a column like by itself. So you subtract, you get this value, and then you keep continuing, and you actually find the same value at the end. Okay, so hopefully by now all of these things are very clear. And if I give you any cash flow diagram and ask you to find the future worth, you're going to be able to do so. Here's one more example. This is more of a fun example. So all the way back in 1626, the Native Americans who lived in Manhattan sold the island to some guy for $24. Of course, because it's 1626, $24 may have been worth a lot more than it is today. But of course, this is hypothetical. This is not a real example. They're saying if they took this $24 and if they saved just $1 from it, if they put it in a bank account or in a savings account, and let's say they would have gotten 8% interest every single year, how much would their descendants, of course they would be dead because this is all the way back at 1626, so how much would their descendants have now in total? Right? And then it asks another question, and it says, in the year 2019, the total US population was about 330 million people. If you take the amount that you would get had you invested $1 from 1626 all the way to today, if you take that amount and divide it equally among the population, how much would each person receive? Okay, someone's asking if there is voice, and someone said yes. So I'm assuming everything's okay on my end at least. And I'll just continue. Okay, so how do we solve this problem? It's sort of the same thing. We're given P as $1. Now N is going to be, assuming we're in 2020, so it's going to be 394 years. You can just add 1 if you want 2021, right? So this is going to be 2020 minus the 1626 that we saw in the previous slide. And I is 8%. And we need to find F, the future value. How do we do that? Plug in the numbers, and you see the amount here, which is huge, astronomical, right? And so this is 14,755,694,7,300,610.78. And you see here, even though the interest rate, I mean, it's kind of high, but it's not that high. It's 8%. But if your money keeps growing year on year on year for 394 years, it's kind of $1. So again, I remind you of the Einstein quote when he said, like, compound interest is one of the most powerful forces, the most powerful force in the universe. Now, for the second part of the question, if I economic equivalence between two different cash flows. Question. Oh, Sultan?
دكتور
Yes.
دكتور ترى طلع من عندك من قبل دقيقتين كذا فصل توك ترجع.
Oh, really?
Yeah.
Oh, okay. So.
عند المثال حق 2020.
Oh, okay. Oh, wow. Interesting.
تقريبا
I didn't-
دقيقتين.
So was this the
وصلنا
last thing?
الاماونت بير بيرسون.
هنا.
Okay, yeah. So luckily I haven't covered much beyond this. Yeah, I mean, it's kind of interesting that I didn't see anything that let me know that I left. Actually, so one thing I can do, but I only have a small screen, is to put Blackboard, maybe minimize it, instead of just looking at my slide. Yes.
can you see the chat?
Yes, I can see it now. Yeah.
Okay, so
I couldn't
can-
see it. So when I'm
Right.
presenting, I usually can't see it, and so that's what I'm trying to do. If I had a second screen, it would be much easier. But I'll try my best to minimize the chat maybe so I can still see it, and that way I can see what's happening. Okay. So yeah, so the last thing I did was I showed you the amount, and then I divided this amount equally over 330 million people of the United States, and we saw that each person is going to get 44,000 and roughly $45,000 per person. So this just it shows you the power of compound interest. Okay. And so then I started talking about economic equivalence. And so this is another central concept in this chapter. And basically, it's going to answer the question, how do we compare two different money transactions? And so we saw in the lottery example that sometimes you would have two options, two different cash flows, two different amounts of money, for example, at different points in time. And we need a way to compare these, right? And so if I give you option 1 is $1,000 a year from now, and option 3 is $1,200, option 2, sorry, is $1,200 3 years from now, which one would you choose? And you can already maybe sort of jump ahead and see how we're going to do this based on the tools that we've developed together so far. And so that's what the concept of economic equivalence. Here's another example. And so I may give you two options and ask you which one you prefer. And you need a way of comparing these two options. And so again, that's what economic equivalence is going to try and do. Okay. Hopefully everyone's still with me.
Yes.
Okay, good. All right, so the first question that we want to answer is, what do we mean by economic equivalence? Why do we need to have this concept? And then we need to answer how we're going to do it. Like, how are we going to establish economic equivalence between two different alternatives, two different cash flows? So what do I mean by economic equivalence? Hopefully it's in the name. So what I mean is that if you have two different options or two different cash flows that have the same economic effect, those cash flows might look very different from each other. But really, if you factor in interest and the present worth and the future worth of those payments, they may actually be the same, even though they look very different. And so, in effect, because they have the same economic effect, you're actually indifferent between those two alternatives. Two or more. I mean, they can be three, they can be four, but generally speaking, we'll have two alternatives. So if those two alternatives have the same economic effect, and we'll see what that means, then you're indifferent between them, and you can actually trade one for the other because they're kind of the same. And so any cash flow, either single payment or series of payments, we can convert it to some equivalent cash flow at any point in time that we wish. We kind of already saw that, right? We saw we had a present payment, and then we converted that into the future payment. So the future one was an equivalent cash flow because the interest rate made the two equivalent. We're going to see a little bit more about that in the next slide, actually. Maybe it's not wise to jump ahead. So again, even though the amounts and the timings of the cash flows may look very different, but what makes them equivalent is actually the interest rate, is actually I. And sometimes the interest rate is called the discount rate. So just be aware of that. So if you hear the word discount rate, it's referring to the same thing as the interest rate. And so here's what I was trying to draw. Here's what we did before. We had a present value, so we had an investment that we made at time 0. And we saw that using the formula, we can move this to find the future value, right? This is what this arrow here is doing. Now, what is this saying? It's saying that this future value that we found is equivalent to the present value given an interest rate I, right? Because you can move things back, and you can move things forward, and you can move things back using the same interest rate and the same number of time periods. And that's what this picture is showing. So from P, we went and moved the 1 at time 0 to F. We applied the formula. And you can also move things back. And so you can take F and move it back and get P from the same formula, except it's you solve for P instead of solving for F. And the only difference here is that you have a minus. So if you move things to the future from left to right, then the exponent should be positive. And then if you move things back from right to left, then the exponent should be negative. That's the only difference. But the important thing here in this slide is not the plus and the minus. It's the concept, right? It's showing that this present payment, P, is equivalent by this formula to a future value, F. Why is it equivalent? Because of the interest rate. And again, the future value is equivalent to the present value, again, using this formula, right? So this is economic equivalence for a single payment example. And you can generalize this concept to when you have more payments, sort of when you have arrows all over the place. It's kind of the same thing. You're moving money between different points in time, but the amount of money that you're moving, the value is still the same. Why? Because you have interest. Okay, so actually this is not working for me, so I'll need to solve this problem of being able to view the chat and look at the presentation at the same time. But at the moment, what I'm doing is not working, so I hope I don't lose you. I'll keep checking periodically just to make sure you guys are still there. So here's a problem. So we have 8% interest. What is the equivalent worth of $2,000 and $2,042 now in 5 years? So this is kind of the same thing that we've been doing, right? You're investing $2,042 now, and in 5 years you're going to withdraw it. And if the interest is 8%, how much is F? So what is the equivalent worth of this amount today in 5 years? That's another way of asking the same question. And you see here the word equivalent. How do we do that? Well, you just apply the formula. This one is a very straightforward example, right? And you apply the formula and you find that it's 3,000. So again, what this is saying is that $2,042 today is worth or is equivalent to $3,000 in 5 years from now. All right? Here's another example. So if I give you two options, if I tell you you can receive $1,500 today, or you can receive $2,007 five years from now. The question here is phrased a little bit differently. It's asking at what interest rate, right? So you need to solve for I. At what interest rate would these two payments be equivalent, right? And so if you think about it, you can frame the problem as follows. The problem is saying, suppose I take the $1,500 today and I invest it at some interest rate I. When will it be worth $2,007 5 years from now? That's how these two payments would be equivalent, right? And so in order to do that, you can sketch it as follows. You can say I'm going to deposit the $1,500 today with some interest rate I. In 5 years, I want to withdraw exactly to 2007. And I need to find I that makes these two things equivalent. Okay?
So it's not when, it's at what interest rate? Because we have the years.
Yes, I didn't get the first part. You said it's not one?
It's not when. So
What
it's
do you
not
mean
asking
it's not?
like, it's not when will I get 2,000, it's at what interest rate.
Oh. Yes, yeah. I heard one, like the number one.
Oh no,
yeah, sorry.
WH,
So,
yeah.
I got you now. Yeah, so this is not asking when. It's saying because you're given two options, right? And the options already have the time periods. You're sort of asking the question, if I take the option that is today and invest it, what is the interest rate that's going to make me get exactly $2,007 5 years from now? So this is not a question of when. It's a question of what is the interest rate that would make the two equal. Okay? And so if you think about it, I'm given P, and I'm also given F in this case. I'm also given N. And so I have 3 of the 4 components of the formula. So can I solve for I? Absolutely. And so this is what it looks like. F equals, so I'll write down the formula just in case you haven't gotten used to it yet. So this is what the formula looks like. And you can see here, maybe we can just do it together here. If you want to solve for I, one thing you can do is, well, first of all, you divide by P on both sides, right? So you get this. Okay. And then what you need to do, or one way of doing things, is to raise this to the power 1n, 1 over n. So you can, I don't have a lot of space, unfortunately, so I'm just going to put it up here. So this gets rid of the exponent. And I can do the same thing here on both sides, right? And then after I do that, I get the following. I get f over p to the 1nth, and I get a 1 plus I here. And then I can subtract the 1. And so I is going to be equal to f over p to the 1nth minus 1, which is exactly what you see here. And so you can just plug in, you have f, you have p, and then you find I is equal to 6%. So now let's backtrack. So we found I. That makes the 2 payments equivalent. So again, what are we saying? We're saying that if I take option 1, so let me go back here. If I take option 1, if I take the money today and invest it, if the interest rate is going to be 6%, then I will withdraw exactly $2,007 5 years from now. So that makes these 2 options exactly equivalent because the interest rate is 6%. Now let me ask you this, based on what I just said, what should I do if I turns out to be, or if I know that I is less than 6%? Right, so just look at these numbers, and if I is less than 6%, what should I do? Which option should I choose?
To take it now and invest it yourself.
Why?
Because you may get more than 6% elsewhere.
No, we're saying the interest rate is going to be less than 6%. We know that.
We'll take the 2000.
Say that again, sorry?
We'll take the 2007.
Yes. Why?
Because if it's less than 6%, we will get less than 2000 after 5 years.
Exactly. So hopefully everyone sees that. So if the interest rate is less than 6%, so remember, 6% is the point at which these 2 alternatives become equal. They're equivalent to me. If the interest rate is less than 6%, that means if I take this money and invest it, I'm not going to be able to reach the $2,007 5 years from now. Okay?
Doctor,
So that's why I should prefer the $2,007 5 years from now. Yes?
what about the inflation?
So inflation, if you remember, one of our assumptions is that 6%, this figure already has the inflation in it. So you don't have to worry about that.
Is it
Right?
known?
So inflation is it what? Sorry?
Is it known now? Is there any statistic for inflation in the world, or?
Economists compute the value or the percentage of inflation. It's just an estimate, roughly speaking. I'm not sure how exactly they do it, but you can look it up for different countries. I think somewhere, if you just Google inflation rate for Saudi, for the US, you will find a percentage, and maybe you will find multiple estimates sometimes depending on the agencies that are doing the estimation. But for the purposes of our course, as we said, unless we state otherwise, inflation is already in here. So you can think about maybe that your money earns maybe 10%, but maybe inflation is 4%. And that's how we get the 6%. Roughly speaking, this is kind of what's happening here. So inflation is already in the 6%, so you don't have to worry about it. Now this is not actually mathematically accurate, but you can think about it this way, right? So your money earns at a rate of 10%, but it loses value at a rate of 4%. So the effective interest rate is 6%. So we don't need to worry about inflation is the bottom line, unless we actually tell you in the problem that you should worry about it and compute it in a different way, for example. Okay, so let me just check the chat. Yeah, so Sultan is having issues with audio for some reason. but everyone else seems to be okay. Okay, so we said if the interest rate is less than 6%, I'm not going to be able to have $2,007 in 5 years from now. So I should choose, because it's going to be less, I should choose the $2,007 5 years from now because that's the option. Similarly, if the interest rate is actually greater than 6%, then I would prefer the money now because I can take it, I can invest it, and after 5 years, I would have a lot more, hopefully, than $2,007, right? If I is lower, then hopefully you even see this from the formula. So if you lower I, but you want to keep F the same, assuming N is the same, what do you need to do to P?
Increase
so
it.
Increase.
Yes, yes. So P should increase in order to keep F the same, right? Because F grows is proportional to P and I and N. The bigger all of these quantities are, the bigger F is. So if you make one smaller, you would have to compensate for it in order to get the same value. So if the interest rate is lower, then the amount that you invest has to be higher in order for it to be equivalent to the future amount. Okay? And so here's an example. If I is 4%, then in order for you to get F equals to 2007 in 5 years, you would have to invest 1650, which is higher than the 1500, right? Because you're lowering interest rate, you want to keep F fixed, you have to increase P. It's just kind of a note, just to keep in mind. So how do we do equivalence calculations? The first thing that we need to do is we want to determine a base for our comparison. Remember, we said we can compare money, we can compare different amounts at the same point in time. What that point of time is, it's up to us to choose it. I can compare the money at this point in time, for example, if I want to. So that means I would have to move this payment all the way back here and maybe move this payment here if I wanted to compare them, for example. I can compare them at time 0, or I can compare them at time 5. I just have to pick some base period for my comparison and then move everything to that base period. Okay? The interest rate is normally going to be given. I just need to identify the rate from the problem. And then I need to calculate how much is the equivalent value of whatever payment I'm moving in that base time period. And we're going to see examples in detail. Now, generally speaking, we're normally going to compare things either today at time 0 or at the end of the investment horizon, so at time 5. That's generally the way we're going to go about things, but you can pick any time period in between and move everything to that time period in order for you to make your comparison. The result is going to be the same. Remember, because all of these are just doing equivalent things. You're just moving things back and forth, but in each step, the amount or the value of the amount is going to be equivalent because of the formulas that we have. And so here's an example about this. So let's say you have this cash flow diagram. So you have all of these payments, and they're uneven. They're not the same. It's just a different payment every year. Let's say I tell you I want you to compute the equivalent amount at n equals 3. So at time period 3, I want you to find how much are these payments going to be worth at time period 3, right? So this is what it's asking us to do. It is asking us to combine everything at time period 3 and then find the value at V3, for example. Here, I'm not sure why they chose V. You can put any letter you want. Maybe because it's not really in the future. It's not like the end one. It's not really in the present. So they just used value, V for value. Okay? And the interest rate is going to be 10%. So again, our base period here is 3. So we want to move everything to time period 3. How do we move things? Well, we already said if we're moving left to right, we apply the formula and the exponent is going to be positive. If we're moving right to left, then the exponent is going to be negative. So here, I need to move this to the left.
Doctor, the screen is frozen or just me?
Things look okay on my end. Can someone else confirm whether or not the screen is frozen? I'll just keep writing.
It is on economic equivalence.
No, it's good actually for me. There's the diagram and you're drawing something.
Yeah, okay. So maybe you just need to restart or like refresh the browser. Okay, so I'll continue just in the interest of time. So we want to move the one at time 0 3 time periods ahead, right? So the 100 is going to be moved 3 time periods because I want everything to be moved to time period 3. And similarly here, I'm going to move this 2 time periods ahead, and then this I'm going to move 1 time period ahead. What about these over here? I need to move them back for 2 time periods for this one, and then 1 time period for this one. And then at the end, I have everything in 1 time period, so I can just sum everything, and that will give me what I need. And so we're going to see this here in detail. So step 1 is to move these guys. So 100, you move it for 3 time periods. Interest rate is 10%. The 80 for 2 time periods, and finally the 120 for 1 time period. And then of course you need to add the one that's there. You don't need to do to move it. So it's just you're just adding the number, the value at that time period. And so this gives you these payments. Now of course we need to do these 2 over here. And so that's what's given here. See, the exponent is negative. For the 200, you're moving it back 1 time period. And then for the 100, you're moving it back 2 times. That's why this is -2. And then you get 264. And finally, keeps happening, then I'll have to make a switch. Okay, so hopefully you followed at least what I was saying here. If not, I was just saying that in order to pick a base time period, pick the one that gives you the least trouble. That means you're going to have to make the least amount of calculations for. So if you already have a payment at 1 and you want to compare it to a payment at 3, just move the 3 to 1 instead of moving both of them to time period 2. Okay, so that's the point of this slide. And also, like, we want to solve this example, so it's asking if you're given, so let me just remove the pen so you can see the example. If you're given these 2 options, at what interest rate are they equivalent? So it's very similar to what we saw before, so I'm just going to go over it very quickly. Here they actually picked time period 3 as the base time period. So this one they don't need to do anything with. This one they need to move it forward for 2 time periods. Right? How do we do that? Again, it's applying the formula with a positive exponent because it's left to right. And then you could solve for I. Now here actually they're using another approach to solve for I. And so the approach they're using is that once they have like a thing that looks like this, what we did before was the following. We took everything to the power 1/2 or 1 over capital N, which is fine and it gives you the same answer. What they're doing here is that they're using logs or lins on both sides. So just to walk you through what's happening here, so they have this. And then if you take ln on both sides, right, so I should have left some space, you get this. But we know that with logs and lins, the exponent can come before, you can take it out and it can come before the ln, which is what is happening here. So you're going to get 2 ln 1 plus I equals, and then you can compute this value, ln 1.2. which is what they're doing here. So that's kind of another way to solve this type of problem. And then after you're done, once you got rid of the exponent, you can just raise everything to the power e. And so what that means is that you get 1 plus I is equal to e to the power of this. And then you can solve for I by just subtracting 1 and you get your interest rate. In this case, it's 9.54%. That's the interest rate that's going to make them both options equivalent. Okay, so I don't have a lot of time. I'm just going to start this because I anticipated that I will finish these next 4 or 5 slides, but apparently not. But fairly quickly, if you have a single cash flow, so we're going to see the difference later between single cash flow versus equal payments versus a gradient series. So these are 3 different types of cash flows. You can think about them as special cases. We're going to derive formulas for them that will give you shortcuts. So once you see them, you can just apply the formula without having to move every payment individually, especially in these cases where we have multiple payments. In this case, it's actually pretty much what we saw before. So I may go over this fairly quickly. So we have a single payment, right? So at time 0. And then you're going to withdraw that payment after accumulating interest for n time periods. And we already said that we can write this thing here using factor notation, which we can find in tables. And so this factor, because you're compounding interest from one time period to the next, right, for n time periods, we call this the compound amount factor. So what is this factor? It's basically the following. It's basically you want to find f given p with an interest rate of I and n, which is equal to 1 plus I to the n. We already know that. So this is called, another name for this part is called the compound amount factor. Okay? And I already showed you how to find this value using a table. You look for the interest rate, and then you look down in the compound amount factor column, which is f given p I n, and you find the value if you need to. Or you can just use a calculator like normal people. So here's an example. I'm going to skip over this because I already we've seen this sort of example plenty of times. It's just saying that you can either use the formula or use factor notation and look it up from a table, which I kind of already told you. The answer should be the same. The opposite is going to be the present worth factor. And so this is going to be P given F. You want to find the present worth of something given a future amount. Right? And so this is the single payment present worth factor, sometimes called the discount factor. It's the same sort of thing, it's just backwards. And you can also find it in a table. So if you look at the table, where is the table? If you look at the table here, this is the present worth factor. It's just P given F. It's the opposite. So you can find it the same way, or you can just use the formula, which again, I showed you already is this, with a negative exponent. Okay? And so just fairly quickly, again, a very simple example that you can go over in your own time. We've already seen this. You can move this future payment back to the present for 8 time periods. So you have to raise it to -8, and you get the amount. Or you can look up the value for this part using a table. Okay, so I'm out of time. So there are a couple more examples. Maybe we'll just go over them briefly at the beginning of next class. And then after that, we'll start the next part of this chapter, which is talking about equal payment series. Okay, so I'll stop here. Hopefully you're all still here. Yep, you are. Okay, yes. It looks like it. And so I'll see you guys next week. I hope you have a good weekend. Yeah, and I'll take questions after I stop recording.